Hello everyone, and welcome to this example recording on the source-free RL circuit. So the example that we're going to be looking at reads as follows. For the circuit below, find Ix for t greater than 0. So we need to determine the output current for t greater than 0. So first step is to determine what type of circuit you have and what type of response you're going to get. So we can see that we have a source that's connected, but at time t equal to 0, the switch opens. So a source is suddenly disconnected at time t is equals to 0. So we know that then we have a source-free RL circuit. And as a result of that, we should then know that the response is going to be a current response because you have an inductor, and that current is going to be I as a function of t is going to give you I0 e to the negative t over tau. So we need to determine the initial current I0, we need to determine the time constant tau, which we know is equals to L over R. Therefore, we need to get the equivalent inductance and the equivalent resistance. Alright, so let's start off with the initial current. So when time t is equals to 0 negative, what happens? We know that the circuit is still active. In other words, the source is still connected. We also know that it's a DC source of 30 volts. Right, it's a DC source of 30 volts. This is 6 ohms, 3 ohms, and 5 ohms. And then we've got an inductor which we know under DC conditions must become a short circuit. And we're looking for that current. Now, how are we going to find this current? So typically the only way we would, or not the only way, but one of the ways that we can find that current would be to first put together these resistances and get the total current that flows in the circuit, and then we can apply current division to determine the actual current I0. So let's say let's start off by saying the 10 ohm in parallel with the 5 ohm. What is that going to give us? That will be 10 inverse plus 5 inverse. Right, that gives us a final value of 3,333 ohms. So we have effectively a source that will have 3 resistances. That is 3 ohms, that's 5 ohms, and 3,33 ohms, and 30 volts. So the current that would flow there, we call it I, must give us 30 volts divided by 5 plus 3 plus 3,33. So 30 divided by 5 plus 3 plus 3,333. That gives us a current of 2,647 amps. Now we can then determine the current Ix. So Ix must give us 5 over 5 plus 10 multiplied by 2,647 amps. That's current division. So we multiply that by 5 over 5 plus 10. and that gives us a current value of 0.88 amps. Right, so that is the initial current. So I0 is going to give you 0.88 amps. Now we need to determine when time t is greater than 0, we need to first determine the equivalent resistance. So at time t is greater than 0, we know that the circuit, this part of the circuit disconnects, so this whole part falls away, and what we have left is the inductor and the two resistors. And if we try to determine the inductance, with reference to the element that you're going to get the response over, which is the inductance, if we try to get the resistance with respect to that, then we can take out that inductance and determine the equivalent resistance. So that's 5 and that's 10, and we can see that the 5 and the 10 are connected in series with each other. Therefore R equivalent, which is RTH, must give you 10 plus 5, which gives you 15 ohms. And we know that L equivalent is equal to the 9 henries, as there's only one inductor, so it's equals to 9 henries. Finally, we can say the current IT is equals to I0 e to the negative t over tau, right? Where tau is equals to L over R, which is 9 over 15, and that will give us a value of 0.6. So 0.6 seconds. Therefore IT is equals to 0.88 e to the negative t over 0.6, and that will be amps. And this is our current response for the circuit that was provided. Thank you for watching this video and enjoy the course.